Starting off week 20, part 2, question 8. The question essentially just asks us to add the amplitudes of two waves, and this can be done very simply by just adding them together. Also, if you go into the graphing calculator like this one here, you can see how the two waves exist independently, but when you add them together, you add their amplitudes, and that's pretty much it. Question 9 is very similar to question 8. In this case, they just interfere destructively, so you just take away their amplitudes, and that's pretty much it. You can see how it's done here in the graphic calculator. Moving on to question 10. By what factor is the amplitude for constructive interference larger than the amplitude for destructive interference? I'd say the keyword here is factor. When I think of factor, I think multiply. So we're essentially finding by how much you need to multiply one wave to get another, or by what factor it's bigger in the other. So the maths for this is quite simple. It's just 9.4 equals 3.2 by some factor. Then you just do the algebra and you get 2.94, which is the answer for me. Alright, for question 11, you just gotta know what a node and antinode is and what a wavelength is. And it's not too complicated. So a wavelength is crest to crest or trot to trot, or every second node, and the antinode is up top or at the bottom, and a node is just where the sine wave or wave intersects the x-axis. So you can see there are the four sections, the sections where it's up lines, sidewards, up, sidewards. So it's just a quarter there between an antinode and a node, and that's pretty much it. Alright, moving on to question 12. A string is stretched with a tension of 120 newtons. The string has a mass of 10 grams and has a length of 2.5 meters. The velocity of wave propagation along the string is, then you're given a bunch of options and you gotta find the right option. Of course, this is a multiple choice which you can redo, so obviously you can just guess the answer, but if you care, here's how to solve it. Alright, before I even start doing the question, I'm going to write myself out a data sheet, which I do for most questions in physics. I just find it useful to have the information in front of me. It prevents you looking back and forth from the page to the question sheet. I just like them in general. Secondly, you find a relevant formula or formulas, and then you get to solving. So for the calculations, I found a formula: velocity equals square root of force over mu. Mu is the linear density, and the linear density is just how much mass there is per unit length. And then I just plug it into the formula, I get my answer, and I always remember my meters per second because you'll lose marks if you don't do that in an exam. And that's it. Alright, moving on to question 13, you can read it there, pause the video. So I immediately start off with a data sheet, because that's what I usually do. I have length, tension, my linear density and frequency, and I just look for a formula that has all four of those things. I found this formula from my log tables, or just Google, or just by remembering it, or just whatever. And it's the same formula we used last time, except it's divided by 2L this time. So we put our numbers in, we get our answer, and that's pretty much it. Alright, but why can we take a formula for the velocity of a wave, divided by 2L, and suddenly it's a formula for the frequency or hertz? Well, the explanation I have for this, and the explanation that's going to help me remember this for the exam, is, for example, if you have a string, right, and the wave is traveling back and forth on it with a certain velocity, then we can calculate the hertz by just dividing by 2L. Since if you have a point L, A on the string, and the wave is traveling down the string and then hits back, and then it reaches point A, if you remember, hertz is the amount of times a wave passes a particular stationary point on a string, you can find that the wave has to travel down the string twice before it reaches a point A. and I think this is true for any point on the line, and that's why you can take the formula for velocity of a wave on a string and change it to a formula for the frequency of a wave on a string, I think. Question 14 is very easy. Just get the numbers. There's a simple formula, you put them in, and that's it. Alright, question 15. Two guitar strings under the same tension have the same length. If their fundamental frequencies and a ratio of 3 to 2, what is the ratio of their masses? Now to solve this question, you can just know that if you square the ratio of fundamental frequencies, you can get the ratio of masses. But I didn't know this until after solving the question, so I ended up solving it with maths. And this is what I like about physics, because you can turn up to a physics exam or know completely nothing with a completely empty head, and you can still figure out what to do. You can't do the same in the biology exam, at least without being arrested. How I solved question 15 is, first of all, I made a data sheet, and I thought, alright, what formula do all of these four numbers fall into? And there isn't much formulas in this chapter, so it was just the one we've been using quite a bit. And I thought, since the frequencies, that's not an equal sign, that's two dots, so I'll rewrite that. So if 2f corresponds to 3f, and we know from the previous question, or the one before that, that f is that formula, we can just replace f with that formula, and we get these two, we get this equation, or this correspondence. I guess it would be a bit more correct to replace the equals with two dots. So now to solve this, we cross out the two L's, we square both sides, so we square both sides, and then 4 is 2 over L. We cross out the L's, we divide by T, and now we're left with 4m1, which is the m, corresponds to 9m2. So now the ratio is 4 is to 9, which is the answer. So now we're done week 20 for physics homework. I hope you found that useful.